invite Dr. Atanu Raha to speak a few words about Dr. Srilekha Raha and her memory.
Dr. Chakraborty, anyway. Yes, good afternoon, all of you. First of all, I'm really grateful to Professor Ritaban Chattopadhyay and Professor Sujitana Chatterjee for giving me this opportunity to be here with you in connection with a presentation of an invited lecture by Professor Supriya Chakraborty. And I'm really grateful to you also, Professor Chakraborty, that during your very short stay in India, you had readily agreed to deliver this lecture on my request. And I thought that, let this room be used because the School of Astrophysics had decided to make this room a place of memory for my wife, who was a student of Presidency College, Lidar Presidency College. In fact, we studied together. My department was physics and her department was botany on this side. And accidentally we met because of exchange of the practical lab papers.
Chemistry, you have passed chemistry together.
We had chemistry A that time. It was chemistry over there. And accidentally our
he knows the history pretty well.
And we have till we studied in college, we were friends absolutely. Just like all our friends here. And it turned out to be a different story. So we were together for 50 years. But during the COVID period, actually, she suddenly passed away, not because of COVID, but for some other comorbidity. She had a high blood sugar. She was teaching microbiology to MSc and BTech students of Techno Indian University. Before that one, she was teaching in Loreto College. And anyway, so I thought that, she was an out and out academician. So her first time, she had to choose between different options. She will be choosing academics or teaching as the first one. And so I thought that, to remember her, I must do something which will remain amongst her students, direct or indirect students. And I chose present Presidency University as the first place to start such work. So I had approached the HOD of Life Science Department, Professor Praveen Mukherjee, and the faculty, and they readily agreed to convert their lecture theatre where she used to attend the classes regularly into a smart classroom. Then I thought that this is my college, this is my alma mater, and during the last 4 years, I had been to USA to my son many times. I've been visiting different universities, and I found that everywhere, be it Harvard or Wharton or Stanford or Berkeley, everywhere they were thriving and surviving on the donations from their alumni. And there the donations come starting from $10,000 to $1 billion. But all are donors and they have Hall of Fames for this one. So I thought that, why don't we do something also here in India, not in Presidency, but in other few places like IITs and St. Xavier's. So the alumni, they donate a lot of money for the development. And here also, our present Presidency Alumni Association have started doing that one. All of you know that one of our alumnus, Mr. Arinda Mitra, he donated a lot of money to construct the computer room. I'm also trying to do my bit, very small amount. I'm a retired IFS officer, so naturally I don't have much budget. But whatever I can do, instead of visiting USA once, I'll try to donate that money for the students here. So, and when I approached my physics department, I did not know that there are two schools of astrophysics and physics. So, and I was very happy to find the very positive-minded couple, Suchetana, Ritaban, they readily agreed to participate in a very small dream project. We have this one, and then in physics department also we have done it. I met your Vice Chancellor yesterday also, he was very positive. I told him that Astrophysics is organizing this invited lecture. And he also told me that we have a lot of other things to think about, we can think in future. And anyway, so with my gratitude again to the School of Astrophysics and to Professor Supriya Chakraborty, and to all the other faculties and the research scholars and students of School of Astrophysics. I would like to thank you again for basically helping me to remember my life. Thank you very much.
Okay, so should we move on to the lecture now? Okay. So it's our great pleasure to have Professor Supriya Chakraborty as our speaker today. Professor Chakraborty did his undergrad from the famous Bengal Engineering College in Shibpur. And from there, he went to University of California in Berkeley for his PhD. That is when he started working on instruments, building instruments that will be used for space-related observations. And after finishing his PhD, he continued at Berkeley as a senior fellow and finally joined the joined the faculty of joined the astronomy faculty at Boston University in 1992. And there he was a faculty member as well as the director of the Center for Space Physics. And his expertise in research is building instruments for various space-related observations. And he's a very versatile, his expertise is very versatile in the sense that his instrument could be used in a balloon, flown in a balloon or in a sounding rocket or in a satellite. And it could be used for observations of the upper atmosphere of the Earth or in the solar, some phenomena in the solar system, exoplanets, as well as the interstellar medium. And in 2012, he and part of his group at Boston University moved to University of Massachusetts Lowell, where he is a professor in the Department of Physics and Applied Physics, as well as the founding director of the Lowell Center for Space Science and Technology. And he is there. He has continued this same line of research, as well as there's a large group of both undergrad and graduate students, as well as postdocs and other research faculties and other faculty members who are working with him to build various instruments. Some of you may know that one of our former students, Sunip Mukherjee, he was a graduate student in his in Lowell and recently he finished his PhD and he's continuing to work with him. So we'll hear about some of this work. I was at Boston University from 2003 to 2009. So that's how.
Me. Please.
So I had the good fortune to meet him there and had I had a lot of dinners at his home and a lot of chats in his office. When my research progress was slow, I used to go and complain to him, and he used to tell me that sort of hang in there. And I did. And he has been a very big friend of the presidency physics, department and student as well. We had other exchanges, including Shunip, and we hope to have more in the near and upcoming future. We hope to have more interactions and more exchange of ideas and even personnel. So without getting into too much details, that I can I guess continue to speak as his introduction for half an hour, but I won't do that. So I'll end there, and without further delay, let's hear from Professor Chakraborty. Thank you.
I think you should have continued because I'm going to talk about something I know nothing about. So you never heard anything about geography, forestry, or anything, but here I am. It's the same kind of story of my life. Now I was in BE College learning electronics, and then went somewhere else, and essentially I forgot all my electronics, didn't learn my physics. Now I teach in a physics department. Isn't that great? So that's good. I mean, it's a great life. Now, how many of you know what a Lidar is? No. Okay, good. This is good. All right, what is it?
So it detects motion. It's like I know it from there are LiDAR sensors in the near
In
elevation
cars.
phone, so it can accurately measure the distances and everything
That's right.
with the 3D.
So,
it's
You know,
thousands of lights.
some of you, maybe all of you know something called a radar. So what's the R in the radar for start? Radio. And L in LiDAR is light. That's the only difference, essentially. There are different kinds, but anyway. So that's what this is, and you'll see. We use light to do something about all kinds of stuff. But today I'm going to talk about forestry. All right. Why doesn't it move?
Click on it once.
This thing is frozen.
Okay.
So I think it's that okay business. Okay, here we go.
Okay, so before I talk about this LiDAR that I'm going to talk about, it's all done from the ground, and I'll tell you what they are. But since Professor Chatterjee talked about work in space, I thought I'll talk about that. So when I worked on my PhD instrument, that was one of those. I guarantee you, none of you were born then, so I can lie. You wouldn't know the difference.
So you cannot touch the script, just design that. And if you touch it, it assumes that you are trying to control the computer.
Okay,
That's
so
why
I'll
it's
do
not-
it here. Okay. All right, so this was an Air Force satellite, and we built an instrument. Part of it was classified, so we couldn't know. Other part were something that we could do. I can talk about what that was, but most importantly, do I have to touch the screen?
Again, it has come up that panels. You have to click 1 second.
That has some.
No, it
Okay. So it was actually very interesting. It was one of the first time that I know of we intentionally created space debris. This experiment was a target of a missile launched from an Air Force airplane, and we created a cloud of space. And we can talk about what it is and how we did all of that some other time. But that's what. But after we did all of this, we were at Boston University, and we started thinking, why not companies build their own satellites? What's so different about it? And so we started asking all of those questions. And what we really wanted to do was develop technologies, and I know I was in India. We don't do a lot of experimental work here, especially in the physics department, a lot of theory, world-class theory, but experimental work is left for engineers, and we don't talk engineers and physicists. So we wanted to do this. We're at a university where we're very close to engineering. This research center that Professor Chatterjee mentioned, we had people from College of Sciences and College of Engineering. We were together. So that's why we started thinking about it. So what do? We gather, distinguished, big name thought leaders. That man won the Nobel Prize a few months before I held the meeting. John Mather, our Apollo astronauts. This man, Harrison Schmitt, walked on the moon on the last flight of Apollo. There are others. That man, Jeff Hoffman, a good friend of mine, he made 5 Explorer telescope. And then there are some other people you probably know. Hargreaves, Dyson, and then there are others. So these are the people. You were there, right?
Yes. I remember going back to the astronomy department to bring more people in, because Martin Rees was speaking and there were not enough people.
That's right. So, so Martin Rees, those of you who don't know, was what was it?
সেদিন বোধহয় ও আসার কথা ছিল রয়েছে
Lord, yeah.
সব এসেছে আমার তো ভিডিও নেই ভিডিওটা
No,
দিয়ে
Lord, I'm sorry.
অদিতি সরকার
So, and then there are people like, head of
সব শুনছে এসে
and all kinds of people like that. So we got them together for 2
না
days.
না আমি ডক্টর অদিতি
And,
সরকার
Um,
চেতনা
we,
চ্যাটার্জি
had
শ্রেয়া
all kinds of discussions, some
ঠিক আছে
splinter meetings and so forth. These two guys, nobody knew them. This is
সুপ্রিয় চক্রবর্তী বলছে
in 2007. And the reason we did that was it's a 50.
এমএসসি জিওফিজিক্যাল সায়েন্স
So these two guys, Chris Basujan, which is this guy from Australia,
বলছো পোত পাকা
they formed a company. And that company, after very few years, put most satellites.
গলাটা তো বাঙালি
তো বাইরে থাকলে করবে তোমার মহারাজ কি করছে তুমি গালি মারছো মহারাজকে গালি মারলে তোমার ভালো লাগবে
Air Force. So you
এখন
can
আর
sort
তুমি
of
গালি মেরো না
group of people.
ও যখন এখানে এসে কথা বলবে অনেকেই বলবে আরে সালা কি পোত পাকা তোমার মতো
Somehow I was
আরে
able to
সালা কি
this
কথা
um,
মহারাজ
and have it tell us something. So some products. This is something I'm very proud of. We had a conversation between Eisenhower and Khrushchev,
শোনা যাচ্ছে
not the ones that you think of.
করে যাই
It's Susan Eisenhower, President Eisenhower's granddaughter, Nikita Khrushchev's son. We had them together, had a conversation about what happened.
শোনা যেতে পারে
There was
যেতেই পারে
essentially a space race, I guess. in those days. President Kalam was the key.
লাইভ হচ্ছে তো
I couldn't invite him to the US. Probably one of the first remote
জানি না কিন্তু ডিস্টার্ব হয়েছে
from Rashtrapati Bhavan.
পাকা
And then there was- so then we did another one 10 years later, same idea, 60 years of Sputnik. We had similarly distinguished people, an astronaut who played music with, rock and roll stars on the ground. This man, General Abramson, he started a program called Star Wars in the US. Very controversial, but he was there for both of those meetings. This man, Bob Cabana, and again, an astronaut, he was the head of Kennedy Space Center, where most of these space missions are human space mission launches. Ken Sembach, another good friend of mine, he was the director of Space Telescope Science Institute, and an astrophysicist. So there are people like that. Here is an Indian man, Rahul Narayan. Some of you may or may not have heard. He formed a company called Team Indus. They competed for Google X Prize. And this was to build something to go land on the moon, travel 100 meters or something, and broadcast HD video. None of those, there are 5 finalists and none of them won because there was a deadline by which they had to do it. But, we became friends enough that I invited him to commemorate 50 years of moon landing. And so again, we're fortunate that, very, very distinguished people, President of American Astronomical Society, Chief Scientist of NASA, Rahul, and this man invented something called CubeSat. Anybody heard of what a CubeSat is? Any other? One person. All right, I know. You know that, I know. So please tell everybody what CubeSat is. So they, I'm sorry?
10 centimeters.
10 centimeter cube, right? Okay. So in a fundamental sense, that's a 1 unit of a satellite, smallest unit. Before that, there were no standards for satellite. If you want to build a satellite, you go start over there, whatever you want would be fine. But this man came up with a standard. Have you heard of something called Beanie Babies? No, these are, small stuffed animals that they gave to kids. They came in a acrylic box of 10 centimeter on a side. That was the inspiration for that format of a satellite. 10 centimeter cube, fill it with water, it can weigh 1 kilogram. So they said that's what the standard would be, about a 1 kilogram, 1 liter volume satellite. So that changed everything. Now, today, most satellites that are up there, and there are thousands of them, are of that format. And you can take one of them or put several of them together. I'll try to tell you a little bit later. So from all of that, what we got was this research center. And you can pronounce it in different ways, but you can see this is a satellite, and all the other things are not. So to point out that we do technology, the other things are science. Locust, when there are a swarm of things, that's a. So we wanted to build a swarm of satellites. That's one of those things. But when I give this talk to people at NASA or other funders, I call them low cost. So you have to, we had to learn how to be a salesman, We all need to do that. So what we do science about space, science from space, and then we build tools, whether it's engineering tools or theoretical tools and so forth. So we're a small group of people. We try to do a lot of things. We don't sleep well. So one of the things we do was, we observe from space and validate, develop technologies ourselves, and we validate in space. Before they become $1 billion space mission, we have to do this. So these are called sounding rockets. These are rockets that go up, fly for about 5-7 minutes, collect data for 5-7 minutes, and come down on a parachute, and you get data. But most importantly, these are complex instruments that we build and we validate. And so in this case, it's a telescope in this particular format. It's a 50 centimeter diameter telescope, and all the things, not just optics, electronics, very specific kind of optical system. Let me ask this question. You probably should know this one. Heard of a thing called deluminator?
Harry Potter had something Harry Potter.
What happened? Tell me about this.
That collects Albus Dumbledore.
That's right. The first opening scene of Harry Potter, right? He goes around and clicks this thing and the light goes up. So we built a deluminator in here. And what it's called, of course, we don't say deluminator, but we call it coronagraph. I mean, otherwise nobody will give the kind of money we need. So this particular one is to directly image planets around nearby stars. So what do we know about planets? What's the difference between a star and a planet? And what do we know from, 6th grade?
They move around stars.
Planets don't have their own light, right?
That's the first thing we learned.
That's right. And so they reflect light from the star. But now, in terms of space, the planets are small. As a result, they're very dim, and they're roughly about 1 billion times dimmer than the star. That's one feature. Second feature is, just like car headlights look, they're closer and closer as they go far away. Stars and planets are far away, so they're right on top of one another. So if you want to see any light from this planet, you have to turn off the light of the star or dim it. That's the part of the deluminator. And so we need to do that. And these are two of Professor Chatterjee's classmates at Boston University. And you don't see any other with a doctor in their title in this. This is a place at NASA. Before you fly it, our instruments sat in this part, and the other things are all NASA facilities. And this is called a shake table. Before you launch it, you have to shake it to simulate launch environment to make sure it survives. And this is where the deluminator goes. There are all the electronics and other things. Everything you see here were designed by people like you. And none of them have built anything like this before because they didn't exist. We came up with what they should look like. So we also did some other work. In this case, it's an astrophysical work, since I'm department got to slow some astrophysics stuff, convention. So there's an ultraviolet image of a galaxy. We launched it on this rocket, went up, took a picture. In here, these were mostly technology validation. In here, we got a 4-color image, four UV color images of a galaxy. So we did that. And since then, we've been spending more and more time on our exoplanet work. This is a balloon experiment. The experiment is larger than this room. And both of these are videos, by the way. You can tell this is a video because the time is changing. And in here, if you look carefully, you'll see that the ground is moving, right? So when we launch this balloon, we launch early in the morning when the winds are calm. And to give you some idea, this whole thing, our experiment is about 1,500 pounds, which is 700 kilograms roughly. And the whole thing, other supporting equipment, all those together is 6,000 pounds. So when we carry this up, we carry them up to about 40, 43 kilometers height. You may have heard that there were some Chinese balloons went over the US that got shot down. They were at 12 kilometers. So we're a little higher than that. And if you notice, I don't know how many of you noticed, this picture is at nighttime, right? You see stars. Something changes. Look at that.
Yes.
So balloon, when they fly is, you launch it. In India, we launch balloons from this, not as big, but comparable almost size balloons from Hyderabad. I have launched one in there. Now you launch, and then you don't fill the whole thing. As the pressure goes down, they expand, and then wind takes them wherever the wind goes. Very unpredictable. And to be able to do astrophysics from there is very difficult. And that shows that we can do it. This is about an arc-second pointing stability. Arc-second. Internally, we changed that to, that's too much for us because you can imagine a star is that much brighter than the planet. And if your hands shake when you're taking the image, you don't get any data. So we had to get a milli-arc second. Now, those of you who don't know what a milli-arc second is, that's what James Webb does. And it's at a place very far from the Earth or anything else. There are no disturbance torques, and they do that. We have demonstrated a milli-arc second pointing. That's all engineering challenge. Has nothing to do with astrophysics, but to do the astrophysics, we need that. So we're building tools to prove what we need to do. And this is a very interesting thing. All the telescopes that we built on the ground are imperfect. So when they take images, they look great, just like anything else. But that's not good enough for us. So we have a separate thing called deformable mirrors. This is almost 1,000 individual mirrors that we could move in any different ways to essentially distort the image, distort the mirror, so the distorted image will be perfect. And that's what we are doing here. In here, we have only on this part of the circle, you can see it gets increasingly darker. And what that is doing is creating a region around the star where there is no starlight. And we have demonstrated a 10 to the minus 6, what's called contrast. So light of the planet versus, or light of the region versus that of the star. So that's what we demonstrated. There are many, impressive research centers that have much better than what we have done, but their work is all in the lab. We're the only group in the entire world that has flown it. And we have flown it 4 times, twice on rockets, twice on these balloons. And we have the next one's coming up in September, and we're hoping to take an image of the equivalent of an asteroid belt around a nearby star in that flight. That's easier than taking a star, just a planet. So we're hoping to do that. If we are successful, you'll probably hear it in the news. So that's going to happen this September. If we fail, I'll lose my job. So we have been doing balloon work here. This is on a different type of research. These are two instruments we built while we were at Boston University. We have a colleague who's now the Dean of Sciences at PRL. He made the arrangement, and we launched it from Hyderabad. And this is how these balloons work. You fill, this is the main part of the balloon. And this balloon is to keep this whole train, the entire thing gets filled with the gas in here as they go up. In our case, that balloon, our balloon will fill a football stadium, Eden Gardens. And this is a little smaller than that. And that thing is called the gondola. In this case, that lived in here. And Indian balloons are filled with hydrogen. So I took these pictures. I was pretty far away. So this is what they look like. It goes up like that and then becomes a more regular shape. And this is where all the experiments are.
Is helium more expensive than hydrogen?
Very, very much so. That's the only reason it's done that way. And it's very controlled. There were times you couldn't get helium, those embargo. By the way, feel free to stop me and ask questions. So we also do some ground-based work. This is called a hyperspectral imager, which images as well as gets a spectrum of anything that you want. In this particular case, we're looking at upper atmosphere. The way this works is up and down is the field of view. So you're looking at a large part of the sky, about 80 degrees in the sky. And x-axis is wavelength. And then there are different specific spectral lines. And we do this because if you take the ratios of those two lines, they come from different heights of the atmosphere due to various chemical processes that go on. By taking the ratio, you could say something about, in this particular case, if you're studying aurora, what are the incident energies of these particles? So you can see that things are different when there are aurora in the sky or not. And in this particular case, I don't know if Professor Chatterjee was there or not, but this is Fraunhofer lines. If you look at take a spectrum of the sky during the daytime, all this black line shows up. That's due to the species in the atmosphere that absorbs it. And same thing up and down is the position in the sky. But look at that line. And I've seen things like this before. It goes up and come down. That's an aurora that happened at 3 in the afternoon. It's not that different from 3 in the afternoon here. The sun's up. And auroral light is fainter than starlight. So the fact that we're seeing an aurora during the daytime is an interesting phenomenon. And nobody can do that because this is a very interesting. Why do you want to study this? Well, during the daytime, the sun shines on the atmosphere, creates the ionosphere. The conductivities are different. So if you could do this measurement, then you can see what happens to the upper atmosphere when these kind of things happen. So it's again another tool that we develop. But so that gives you an idea of we are interested in lots of challenges, lots of science. It has to be interesting science, but also it has to pose a technical challenge. So anybody has any questions of anything I talked about so far?
So that is called day glow? That's daytime aurora?
No, day glow is the thing that is always there. So daytime air glow. Air glow is the photochemical reaction produced emissions. We just shipped this instrument to Sweden to study aurora, and the student, an Indian student, took it there. I just got the WhatsApp this morning saying she arrived and getting ready. The instrument hasn't arrived, but she has been there. So
This was taken at Boston, right?
this one, yeah, very rare. And in fact, this year there were auroras seen from Boston even farther south. So
That is related to that, but the aurora seemed pretty south.
yeah.
That was the activity of the sun.
That's right. So auroras, if this is the Earth, auroras happen near the
The pole.
pole, right? And it's centered on the magnetic pole, so it's tilted with respect to the geographic pole. And when the solar activity increases, and it happens on the south hemisphere as well. So this sphere, this circle where you see the aurora expands. And as expand, they go further south in the northern hemisphere and further north in the southern hemisphere. So that's why we saw, and I can show you pictures of aurora I took on my cell phone. Exciting times. Okay, so I'm going to talk about an instrument that we have developed to study forest structure. And so we call it Duel. And I'll give you a little bit of background why you want to do this. So this is from FAO that talks about why you want to know about forests and why you want to study. These are big human questions. So people are trying to map forests. Are they changing? If they are changing, how are they changing? So we got involved in this because I had we're thinking about developing something, and I came to talk to this gentleman, Jagdish Kiswan, who was in the government. He was the Director General of Council of Forestry in India. This was, I forget when I did it, years ago.
2009, I think.
I'm sorry?
2009 or?
Could very well have been.
2009, it says there.
Yeah, that's when he gave the presentation, and I saw this and I got that. So what we did was, how is this done? I think Dr. Raha could tell us about how it's done today. So what it is you can map forests from space, but how well do you know what the forest is made of? You need ground truthing. So this is what is talked about. And the reason is this red is this acronym, UN dictum. So you need to reduce emissions from the forest because all the carbon dioxide that we're putting in the atmosphere, they get taken away by the trees in the forest. So you need to know what that is. And how do you know it? And so there are imaging data from space. And then the key is you go there and what they call ground truthing. So you take an image and the forest might look like what the floor looks like. How do you know what's in that dark part of the forest or over there? So you tell people there, and the way it's done, I've blown up that, you can see somebody goes there with a map and makes very manual measurement. And that's how it's done. And you can imagine how much area of a forest you could cover by doing that. So that's the problem we wanted to solve. And there are two parameters that forestry people measure. One is called DBH, diameter at breast height, and the height of a tree. If you could measure that, most of the carbon is sequestered in the woody part. The leaves don't have much. Please correct me if I'm wrong. It's your science. Yeah. So this is the process. And there's this tool that gives you an estimate of the height of the tree. Those two parameters alone could tell you how much, and people have figured this out because they chop down some trees and weigh it. By weighing it, you can tell how much there is. So you can imagine how time consuming it is, how much error there could be. because, forests are not all flat, there's a slope. So we wanted to do something. And while we were thinking about this article came out in The Economist. They said, well, I have highlighted some words. So this is the old-fashioned way. You take a tape measure and a notebook, you write those things down, and then, and it says, you made a 500 square meter plot, and then you go to another. In India, there were 10.
Water formula.
Huh?
Water formula.
Quarter, there you go. So you can sort of see how infrequently you could do, but still that was the state of the art. And then they talked about there is a new tool, and they use a technique called Lidar. So that's where it came about. So now I will tell you about, Lidar is something that I don't know your name, but you talked about it. You send a pulse of light, you wait for it to come back. Somebody said the speed of light is constant, so if you could measure the time difference, that'll tell you how far away that thing came from. Problem is, you couldn't do that in a forest. You can see as your beam goes, it gets bigger and bigger. You could get reflections from multiple trees. So how do you account for that? That's not very well. So you make the beam narrower and narrower. So you restrict it to a small region. So we came up with something called a full waveform Lidar. And what that means is even when these smart cars and other things, they use Lidars all the time, but they take the strongest return or the first return. So we do something called full waveform, that is multiple returns. This is the same thing about the ground truthing and calibrating. So I am going to skip that. I'm going to show you this. The way, if you fly an airplane, that's much closer, so you could cover larger ground. So if you have a discrete return or the single return Lidar, you send the beam down and then you get the return, and that's what it'll look like if it's a flat land. If it comes from a slope, a conventional Lidar will give you the first return or the brightest one. But if you take a full waveform Lidar, in this case it's flat, so you'll get one return. If it's a full waveform, you'll get a multiple returns that will represent, if you do the math correctly, it will represent the slope. If it goes through a tree, now you get so many different returns, and that's what we wanted to do. So that's why we wanted to use a full waveform Lidar, not just the one return, but it'll allow us multiple returns. We also had a challenge, and that is we wanted to put it on the ground, and we cannot, crank up the power on the Lidar because apparently there are animals in the forest and they have big eyes and they don't want us to blind the animals. So we had to turn down the power, and our Lidar has a range of 100 meters. So foot per nanosecond is what they say is the speed of light, so you can figure out how much you could cover.
Infrared wavelength, or is the wavelength is what, infrared?
Any wavelength will have the same thing, but we did it in near infrared.
But this is for a light.
Right.
For a visible region.
Yeah, it works anywhere. The reason we do it, and I'll show you, the near infrared is cost, because the optical communication people develop solid state lasers, and we wanted to use those because if we wanted to use our one, the big laser, that doesn't work. So that's why, and there was a Lidar that was developed in Australia, CSIRO. They call them echidna because they have this animal called echidna in Australia. It doesn't stand for anything, but it looks exactly like that. Our instrument is exactly like that. And the way it works is you send a pulse and then you scan. So send another pulse there, another. So you do that while you are rotating this whole thing. So as a result, you get the full sphere. So that's what the principle of the observation. Each of those green dots is a laser pulse. And so now you're sending this out. Now the challenge is, what are you receiving? There are the airborne thing is called ELVIS, NASA's Land Vegetation and Ice Sensor. So they do that. They could also do all of these kind of things that we're talking about. And the wavelength is just beyond 1 micron. And this is the most popular wavelength for optical communication. So they had this, and this is what the echidna lidar was. So why did we change things? And the story goes, our colleagues that were at Boston University and the geography department came to me, says, hey, can you build a LiDAR system? I said, yes, without knowing how to spell LiDAR. And then we sort of talked about, they used this instrument. The instrument they used was 60 kilograms, used petrol in a forest to run this thing. As a result, they could not go very far into the forest because the road, you have to carry everything, you need a whole group of Sherpas to carry your instrument. To make matters worse, I asked a stupid question. I said, what would happen if you do more than 1 wavelength? Oh, that would be revolutionary. Why? So I think, this is the technique. Let me show you. These are some of the terminologies that the forestry people use. There's a thing called the leaf area index. You take a camera, take a photo. You could do it that way, or you could take these photos at different heights. Almost, worse in some cases than the other one, which is the 2 parameters that from the ground. But what they're trying to do is taking an image of each of the circles are what they see from different heights as they go. So this is an important parameter, and that's an image from the LiDAR. Same thing, if you compare that with this, you'll see basically same thing, but you get much higher resolution. Things are solidly on the ground. You can take the measurement very quickly. So that's the reason for doing this.
Pulse backing from leaves.
I'm sorry, say that one more time.
You are getting the pulse return even from leaves.
Even from leaf, yeah. In this instrument, you get they don't distinguish between leaf and the woody material because it's one color. Whatever reflects is reflects. Leaf probably has a different reflectance than wood, so you don't know. Nice.
So you are better than a photo because you are getting the third dimension.
Right, you don't get the third dimension. Every image that you get from a LiDAR is an X, Y, and the distance.
And
Every pixel you have.
using the infrared band also.
Yeah, it is.
So there is an added advantage for vegetation with regard to the reflectance. So
Right.
it will be pretty much higher.
Right, that's why my question was, why not, what could we do with a 2 color? And these are the reflectance as a function of wavelength. And this is the 1064. You can sort of see most vegetation has similar reflectance, but in here they're spread out. So if you make measurements in those 2 colors, you could discriminate between various things.
Are they green band and the infrared band?
These are both infrared. This is
No, for the infrared band actually for vegetation patterns versus a conifer and deciduous.
yeah. These are all
There
yeah.
is much better differentiation.
That's right.
But not for the green band.
Right. But the green band would be here.
This green band is somewhere here, 0.55 or 6.
Yeah. So that's why I'm saying.
Very narrow differentiation.
Right. Oh, I touched the screen. I hope it works.
No, you can touch it.
No, but I would,
No,
and this is a simulation of an area where we have different kinds of trees, and you can see now we can distinguish between the woody material, which has all the carbon sequestered, versus the leaves. So that's what we wanted to do.
So it's like a 4-band spectrum.
Exactly. Yeah, for astronomers, oh, you guys we have done it, 50 years ago. But which bands, right? So there were those, and because I do spectroscopy, I asked, when you have one, try and a second one first. So,
And so the reason that we pick those two wavelengths is because is there some peak or something in the reflectors? Because what is the purple line there? The purple line?
purple line is the dead willow foliage.
That is because,
Oh.
can I just,
Please, you're the man, you should be talking.
actually, if you look at vegetation, say from 10 kilometers above, whether it's a conifer trees in the hills or the deciduous trees in the plains, it will look almost same green. The differentiality of the green color is very, very low for the green band. For the blue band, they get scattered, so it's not very useful for vegetation photography. But for the infrared band, it has got an excellent, it's a window, so it passes through the atmosphere.
হ্যাঁ ওই তখন যখন ফোন করলে
But when a red band falls, infrared band falls on two types of vegetations, so they are separated out quite large as compared to the green band. Green band and red band, they're good for
তারপরে
vegetation.
দিকটা নিয়ে এসেছিলাম না এটা তো গত বছর
The graph. So they are the only bands useful for vegetation monitoring. That's all. But for water bodies, infrared band will be basically absorbed by the water.
And
Am I right? Or
রেস্টুরেন্টে খাবে
I'll show you what I know, but
তুই জিজ্ঞেস করতে গ্লিসারিন
so that's why we decided to do this experiment.
One thing just
Huh?
here,
হ্যাঁ
the color we are seeing here, intensity or brightness is different.
Right,
Well,
yes, that's right.
So that is how we are getting.
কার্ডটা দিয়ে দেওয়া হচ্ছে
Right.
তাহলে
There is brightness, but also two different color brightness you can take ratios. You can do all the usual data processing that the astrophysicists do all day long. Right, so this is false color. This is false color because these are both infrared, so it has to be false color. Yeah. So
Color we are get.
হচ্ছে আমি ওই ছেড়ে দিয়ে আমি
like, I'm using only two.
তো তাকিয়ে
To do in Euroband, these are lasers. So, we could do other things, but this is just what we did. We can make, you can actually put one right here. There are many other ways you could do.
yeah.
But this is what we could buy the laser for low cost, et cetera, et cetera. So this is how the data from the EV instrument, which is the same instrument as ours, except we have two different colors. Take a look at this. If you are trying to take a measurement of a tree height, you have to go far away, almost as far away as the height of the tree to make the measurement. It's a simple triangulation, right? With a scope like this, you run into problems. With a Lidar, you don't correct that because it's a 3D image. We could do all the image processing that you need. So this is what it is. This is what we could do. And there are many other things such as this we have done. For example,
Another one thing, for the leader you are taking, so it is taking, maybe it is a UAV. So how much you are?
I'm doing it from the ground. It's not, this is from the ground to provide ground.
এসি লাগানো দিয়ে আমাকে টাকা ফেরত দিয়ে
No, it's on the ground and getting full hemisphere, full hemisphere.
আমার কাছে টাকাটা
Just
ফেরত
like
দেবে
that image, that image.
So this is
So
you have done from the ground.
it's all from the ground. So you don't have to hire an airplane or any of those. And there are problems with the UAV also because the ground also reflects.
Yes, yes.
So there are reasons for doing it this way. So now here is a set of data, same part of the land, 2007, 2010, and you find that it has fewer trees in one case than the other. We can also see in this case, a part of the crown of a tree is missing. So it was after branches broke. So these are the kinds of things, it's very easy for a LiDAR to get. and provide ground truth. There are all kinds of other data that we have, but I didn't bring. But this is an interesting problem that I want to tell you. So in here, we had a little barn in the forest for storing whatever it is. And so we did a sort of multiple position measurement, like so we could do tomography basically to get a three-dimensional pictures from various locations. So those are the areas where we made measurements. And then somebody wanted to study how bats go out to find their food at night. So this is, they put a night vision camera in there.
No,
and,
no, last
this is a flight of a
can
flight
remove or can remove.
a single.
I mean,
And there are many others. So each of these lines are a different.
সব মিলিয়ে আমাকে 2250 টাকা দিতে হবে এর আগে
Some came up, went somewhere else. So it's some biologists. We had at Boston University, there was a professor in the biology department who was very much into studying bats and bat behaviors. So it's not just for forestry in terms of vegetation, but animals in forests are also an important parameter. So here,
Bat flight was caught because the lidar is going on
measuring. So LiDAR measured once.
Okay.
So now you know what the forest looked like. And
Now
then the
it's
night vision camera just did so this is sort of what that kind of thing looks like. I don't know what is in here, but too many music and other things, but so once you do this kind of measurement, this is what you can do with the data. You can now process it in any which way you want. And that luxury you don't have when you're going with a tape measure and a notebook. So you can look at it from different angles. You can, and we have done this with our instrument. We have done it in Massachusetts. There is a fully calibrated forest. There is a region of a forest that has all kinds of instrumentation. They measure some trees with a 1 square meter sort of catcher. So they catch how many leaves fall in there. I don't know enough geography or biology or forestry to talk about those.
in one day how much area you can cover?
So each, it depends upon what resolution you want, but roughly from one place we could get 40 minutes gives you one measurement. So it's a 100 meter square and however 100 meter cube, I guess. So and we have done it in various places, and you can see this is a different part of the forest. When you take a picture from above, they may look similar, but you can sort of see here the trees are different, the densities are different. And so we have done things like that. So these were our goals. We wanted for ground-based measurements, and then we wanted to quantify. These are all fully quantifiable because every pixel has number of, or not, density of leaves and woody material, all of these things. And then you can go back to the same place next year, next month, whatever. And that could also tell you if there has been any changes.
This particular software can be used for the satellite measuring also.
I have not processed any GIS data, so I have no personal experience, but I can almost sort of say it's just software. No, I know it's a very difficult task. It's a very difficult task. Image processing, has moved very far from what I knew. So this is what inside our instrument. I can talk about it all day long, but it has a 4-inch telescope. That's the beam that sends out the data. We have these lasers that we have 2 lasers, but we also put a green laser because we wanted to know which way we're pointing. I had no idea. So we wanted to measure. So there are 3 lasers in here. And this is a mirror that spins. So So it gives a meridian scan like that. And then I rotate and then do this scan. Then I rotate, then do scan. And that's how we cover the entire sphere. But if the instrument sits in a box, I don't get any data on when it goes to the back. So that can be used for calibration and other things. So there are all these parts and all these optics design. We love optics, and I can talk about it all day, but let me not do that. But the key here is all three beams travel in the same path at the same time. And the reason is you could easily have made an instrument that said a red laser takes the data and then come back later, take a green laser, but there might be wind, the leaf might be bent and you wouldn't get the same measurement. So we wanted to make the same measurement for all three colors at the same time. So there are a lot of times we spend thinking about and arguing. So this is the first time we took the instrument in a forest. And most of these people that you see here are students. There are professors like that in there, this man, but everybody else are sort of students. And we like to involve students like this. These two are very young students. He's now a professor in Arizona, doing quite well. So that's the fast spinning, and then the whole thing moves slowly. So that's what the very first day, we didn't cover anything. We just wanted to see how well things work. And then this is the data. In this particular case, the leaves were gone. We went there in winter. This diamond-shaped thing is a directional marker. So we know where, east, west, north, south kind of thing. And then there are some balls that have wavelength calibration or reflectivity calibration. So we have all those things in the sky. And so this is what the raw data look like. I can see when we're looking towards the projection makes them different. But so here is that diamond-shaped thing. And I have to look hard. There are the two directions in here. But what's this? There's that in both pictures.
Sky. There's nothing there.
Bad, but no.
No.
It's the sun.
The sun.
So we could make the measurement during the day. And this is in the infrared. So you have to start getting.
Using the infrared band.
Yeah, both of these are infrared bands. Yeah, not quite thermal, but yeah, very near infrared. But you can also see other differences. In this color, look at this tree, very different, right? So this is how, in astrophysics, you do temperature and other things, color, or whatever they call those things.
With the same equipment, you can generate different bands?
Yeah, that's what this is. So exactly same.
That's the two-wavelength.
Any two bands.
No, I can put more. It's a question of money.
Right now, these are the.
We did this. We did it the first time, and we said just make it 100 times better. So factor 100% better, not 100 times. But anyway, 100%. That's what we did. But now you can also see other things we could do. Now these trees have leaves. Look at that tree in those two colors. What that tells you is in this color, the moisture absorbs this color, right? That's why it's dark. It's not as reflective. And so this is the false color combined. And this one is the normalized difference. You take the difference, divide by the intensities of those two together. This is the most powerful thing. You can now almost count the leaves, almost tell the difference between the leaves and the woody material. So that's what we think. And we stopped doing anything because our part was done building the instrument and testing it. Our colleagues at the geography department continued with the work, And then the Australian people who built their first one using petrol to run it, we sort of used batteries. They forgot that batteries were involved or invented. So we gave them all of those, and now we can make much lighter. It's only about 30 pounds, 2 colors, and we also have Wi-Fi kind of thing, local network, so we could communicate. Because while this is spinning, you don't see any persons, so we sort of run behind the instrument. So we could do that easily when things are small. So that's what we did. So I don't know what I have in here. Oh, you could also do this kind of things. You were asking earlier about taking airborne images. So we could do spectra from airplanes, satellites, however way you do it. These are all complementary.
By the drones also.
Yep, that's right. And so we came up with a simple idea. When you are in a big Maharaja's places, you see windows with different color glasses, right? So we said, we're talking about all different colors. Why don't we put a colored glass window in front of a camera? So what can you do with that? Well, what you can do is, if you make when you take an image with something like that in front of you, when you're looking through this part, you're at one color. When you're looking through this part, you're looking at a different color. But if it's on a drone or a satellite or an airplane, they could move. If they're moving, what you see here will show up in this color a little bit later.
Okay.
Right? So as long as you can assume that things don't change by the time things move, you get multiple color images. So that's what we decided to do. This is the work of one of the physics department graduates. So we're challenged by the team industry, and they said, if we could build an instrument that's 1 kilogram and less than that, I have all these handwritten notes, we will fly it, we'll take it to the moon. And then I said, what do you want it to do? I said, whatever you want. So we wanted to do something like that. This instrument is basically roughly about 10 centimeter and roughly about 4 centimeter or so in height. That's the instrument. Up here is all the electronics. This is the optics, not the instrument. And this is here, has all the electronics, computer interfaces, and so forth. So we built such a thing, looked out the window of our lab. So these are the 4 colors. And it's made for sodium, the same sodium lamp that you see on the streets, and potassium, because in Moon's atmosphere, there is sodium and potassium. So you see these images. I have videos of this that shows how things change. And then what we did was, well, the Google X Prize thing went away. So we put this instrument on one of those big balloons that I showed you earlier and took some images, and those are the images that you see from 2 different heights. So just to show that this idea that we came up with works quite well. So we, like to build optics. So, and this is this just to show you the size of our balloon payload. This whole thing is, all of that flies. These are steel beams. And this man standing, this is Chris, about 6 foot something tall. And that was my only contribution to this project, saying we need to put a sticker of our university. So that's Sunip's instrument. To run it, NASA gave us a huge battery that could probably last us for months, but it was only one night's work. So that's the instrument, compact multi-wavelength imaging camera. I think that's what the name is. So we built it, we flew it, and we got that data. And there are others, But then we had a second flight came up. So we decided to try some other colors. So these are all the different colors that are upper atmospheric, and down below are the Landsat filters. So Landsat, those of you who don't know, is a NASA series of satellites for remote sensing of the ground, different colors, give you, different diagnostics of, crop or water and other things that I don't know about. So we put this, we again did the same test, we flew it, and we got all kinds of data. So now I want to tell you something else, completely different. We got some funding from the state of Massachusetts to build a new facility. It's to do small satellites, these CubeSats that we talked about. And we have all these different partners. And here is the fun part for me, build a new instrument. When we launch this is a CubeSat that's 3U, meaning this is 1 liter, 1 liter, 1 liter. So together it's a 3-liter instrument, 30 centimeter long, 10 centimeter by 10 centimeter in cross section. You could put any combination of that. And when they launch it, they put something in here. There is nothing in here. And they take it to the space station and put a spring, and that spring releases and the satellite goes out. That's how it's launched. And this volume is, in here about 65 centimeter, which is the rectangular part. And this is altogether it's 111. So it's a half of a cube and a cylinder. And again, my only contribution to this project is to come up with a name for this. It's called chickadee because chickadees are kind of a bird, and black-capped chickadee, which is this, is the Massachusetts state bird. But what does birds have to do with satellites? Well, satellites are often called birds, people in the business. So we tried to come up with a new format of satellites that takes advantage of that. And we designed and built it. And in fact, I brought it for you. This is the full-scale model of this. This is why I wanted to have my backpack here. So this is the full-scale model of a satellite. It's way more powerful than many satellites that have flown. And this thing was a 3D printed, of course, was done by an undergraduate student, some just like you, over last summer. These are the solar panels. So when you launch, it goes like this. When they launch from there, the panels move, open up, collect data, collect sunlight. And then what we did was, this is something that has never been done before. This is the entire electronics that you need to run a satellite with an instrument. So there are 4 boards. These are all Sunip's work. So one board does payload processing. So talk with the instrument. We don't care what instrument this is. Another one is communication. We have to collect data and send it down. So another board does that. Third one is attitude control that points it whichever way you want. And fourth one is controls the electrical power system. So you get the data from the, power, sunlight converts into electricity, and then you control it. We even have started building things. And the idea here is each of this board has a processor and makes it very, what's the right word? Standard and uses a language, those of you who are computer types know it's called Rust. And so our goal is to get this thing done as soon as we can. And this part that I showed you before is total waste. Currently, they put a thing that looks like this and launch. And this thing is essentially a space junk. So we said, what happens if we could use this? The spring goes over this. What happens if we could use that? And so that's question led to the creation of this. And we're going to do this. And as I said in here, what we want to do, hands-on education. Imagine you have such a satellite here in this room. You hang it there, you could do communication, you could change the orientation, you could take images, you could do your image processing. This is the other reason I wanted to have the camera on. So the people who are in your techno campus could come up with ideas of what you could do. So this is something that I would like to see in every colleges, or even, there are places in Brazil, for example, middle school teachers, which are before high school, have flown their own satellites. Why couldn't our students do this? So these are sort of questions that led to this. And in itself, this could also do real science, namely the instrument that I showed before fits in this volume. So we have other, cutting edge science that we could do. And there are some other things we could do, if you fly many of them. So with that, thank you. I'm happy to take questions.
We can ask first the online participants if they have questions.
Okay. Okay, anyone who is online, do you have any question?
Unmute yourself and or type the question. Yes, all of them are online, large number of people.
So I don't hear anything.
Sir, we don't have any questions.
Yeah, can you be a little more loud, because we cannot, we can barely hear you.
We don't have any questions.
Okay, you don't, okay, there is no question. Everything is crystal clear.
Yes, sir.
First time, there is first time for everything.
Okay, other questions?
From my side, one question. Actually, it is actually ground-based radar systems is showing very beautiful